घर से निकलते वक्त चाची ने गुस्से से कहा,
सुनो, घर बैठो और प्याज काटो।
पर मैंने सिर्फ प्याज नहीं काटी, अपना पार्लर भी खोला।
टूट रहे हैं, काट दो।
प्याज है,
प्याज?
बाल टूटेंगे नहीं, बढ़ने दो यार। प्याज से बना नया सनसिल्क अनियन शैम्पू, ये पहले वॉश से लंबे बालों का टूटना 90% कम करे।
वंडरफुल, नाइस शॉट।
नो टूटना, ओनली बढ़ना। सनसिल्क।
Guys, target is on the move.
I can see him. काशी, गाड़ी निकाल।
आ रहा हूँ यार।
Move! Hurry up, जल्दी करो।
नदीम, फैसल, सुंबल, काशी, चल सारे का सारा उधार आज ही चुकता करेगा तू। कौन बताओ? PKIBN 472382 चुप कर, मेरे मोबाइल नंबर पे जरा इजी है। लिख 0302 7273। नहीं हुआ। दोबारा लिख PKIBN 47238257। सारी चीज बताया कर यार, मोबाइल नंबर अपने दे यार, मुझे बोलने तो दे।
1 मिनट, स्कैन करो।
हाँ?
Told you, जिंदगी QR से ट्रांजैक्शन करना इंतहाई आसान है। जिंदगी से पैसे रिसीव करना हुआ अब बहुत ही आसान। किसी भी बैंकिंग ऐप से अपनी जिंदगी रास्ट इनेबल्ड QR को स्कैन करो और मनी ट्रांसफर को सिंपल करो। हो गई ना जिंदगी सिंपल।
मैंने भी जिंदगी ऐप इंस्टॉल कर लिया। तो वो अगर वापसी की गाड़ी का किराया मिल जाता तो बोरी का।
All right, hello everyone. We are back trying to talk about metamathematics and its relationship to our physics project. The surprising unification of, in a sense, the dynamics of mathematics and the dynamics of the physical world. And this is the notebook that Jonathan was using last time to talk about the, in a sense, just to summarize, and Jonathan should interrupt me as appropriate, but the basic idea is our multi-way systems can be thought of, the rules, the underlying rules for the multi-way system can be thought of as the, just as they can be thought of as the operation of the rules of physics, they can also be rules of mathematics, that is the application of mathematical axiom systems. And so in a sense, this is, so one interpretation, and again, we need to get these a little bit straight. One interpretation here is that what we're thinking about is theorems show the equivalence between things. So for example, these might be two representations, these might be a representation of a word in a group, and this connection here might say, according to the axioms of the group or groups in general, that word is equivalent to this other word, and therefore there is a theorem that says this is equal to that. And then there is a progression of sort of what's equal to what that you get by following down these paths. And that's kind of, and then the idea is to encode a sort of a base axiom system as the underlying collection of connections here. And I had examples of this even in the NKS book of doing things like that. Then, new idea, the notion is to think about foliations of this graph as corresponding to models of the underlying system. So in other words, we're saying based on the underlying axioms, we can deduce that this turns into this, that this is equal to this, and so on. But now, if we add a model which essentially allows us to, which essentially coordinatizes this picture, this is sort of an arbitrary coordinate system we're using here, but that coordinatizes this picture, then we say that that coordinate system says that anything that's below something else in this picture is follows from or is equal to that. Now, I'm already a little confused here because as soon as we start thinking about, I think we had some foliation somewhere here. Are we imagining in this picture where these things are terms, are we imagining that we're saying that anytime you are essentially going down the orthogonal direction to the foliation, that is an equality relation? Is that Jonathan or Xerxes? Is that what we're saying here, or not?
Well, I mean, this distinction is why I spent so long talking about, clarifying the distinction between the groupoid structure and the topos structure, right? Where one is simply localizable and the other one has isomorphisms everywhere. So in the localizable case, it's possible to turn implications into equalities, but in the groupoid case, it's all the implications are already equalities. That's that's the clarification.
Sorry, say that again. Say that again. For the groupoid case, I understand that what we've done is we've turned every one of these into a two-way thing, right?
Right. So because the sort of fundamental structure that we're dealing with, which is the Rulio multiway system, has a groupoid structure, but by design, so to speak, and because every other structure can be viewed as being either a foliation or a fibration of that Rulio multiway system, they inherit not a full groupoid structure, but a topos structure, in which it's not the case that every morphism is an isomorphism, but it's the case that the topos can be localized, so you can convert a subset of morphisms into isomorphisms.
Okay, So when you say, so generally, these one-way arrows are thought of as like the morphisms of category theory. A two-way arrow is like an isomorphism.
Yes,
now,
exactly.
When you say, okay, so let's just zoom out for a second. The Rulio limit, which I'm claiming is a little bit like some kind of normalization group fixed point or something. The Rulio limit, let's just understand how that arises. The Rulio limit comes when you say, for every one of these, instead of having this particular rule, I'm going to add all possible rules in this case, right? You could think of it. Could you think of it as some kind of completion limit, or can you?
No, that's exactly what it is, right? That's the point. It's as each completion is applying a homotopy, and the Rulio multiway system is what you obtain in the limit as you add progressively higher order homotopies.
Okay, let's walk through that for 1 second. Okay, so each what we're saying here, a homotopy is to say we're going to take that diamond and we're going to crush it, right? That's saying that's what a completion would do. Am I right?
Yeah, so that would be a homotopy for paths of length 2.
Right. Pushx on our live stream is asking about this foliation. This is just a toy example. What we're showing here is just a toy example. This is not a the real thing is much wilder than this.
Right. I have some actual examples in my bulletin.
Okay. Should we look at them? Should we?
Yeah, if you'd like. It's up to you.
Let's do it.
Sorry, let me share.
नेस्ले पाकिस्तान और बेनज़ीर इनकम सपोर्ट प्रोग्राम के ताउन से नेस्ले बिस रूरल वुमेन सेल्स प्रोग्राम बिस की मुस्तहकीन को खुद मुख्तार होने में मदद कर रहा है। ये प्रोग्राम देही खवातीन को सेल्स एजेंट्स बनने की तरबियत दे रहा है ताकि वो रोज़गार कमाकर माली खुद मुख्तारी हासिल कर सकें।
साडा एक्सीडेंट होया है पहले मेहनत मजदूरी करेंदे आसे बहुत मुश्किल वेखण लगी बई वो भी मजदूर हो गया अंगली कटी गई मेरा भी गोडा टूट गया। उस तो बाद असीं दुकान बनाई बाजी आई है नेस्ले वाली सानू दूध सेरिलैक्स जूस ये लिया के दिते शुक्र ते अल्हम्दुलिल्लाह नेस्ले वाले दी तरफों खुआत वाले तो बाजी सानू लोन ला के दिता असीं अपनी दुकान भी अग्गा चलाई बच्चों नूं भी स्कूल भेजिया। नेस्ले अखुआत वालियां दी तरफों असीं बहुत शुक्रिया अदा करते हैं।
on its face would just complete a single branch pair would just remerge a single branch pair. But when we add that rule globally in, it produces this knitting, this more global knitting of those paths.
Well, no, not quite. I mean, so what's happening is you're inducing this is a sequence of critical pair completions you're inducing by defining this homotopy between these paths.
Oh, I see.
Then,
I see. I'm sorry.
Then when you add those in as completion rules, then you get this structure which has that homotopy, but it also has other, more global effects.
Okay. So I was wrong about the level. So I could have.
What I said you were talking about
was right. What you could have done, instead of doing that homotopy between those paths that were of length, whatever they were, 5 or something up there, if you just done the length 2 homotopy, you would have gone. Then you would have still got a globally knitted thing down below, because by implementing that homotopy, you are, as a completion, you're having a global effect on the system.
Yes, but it just wouldn't necessarily have knitted the entire paths
of those particular paths. It would have only. If you had a single diamond, if you had just a one diamond, then it would have knitted that diamond, but not necessarily a bigger diamond.
Exactly. And which pairs of points you consider to be related in this homotopy depends on your foliation, right? I mean, so in this case, we're foliating with respect to the initial cosmological rest frame here. So we're, so this point is associated to that point, this point's associated to that point. But if we picked a tipped foliation, it would be different, as I'll discuss later. And so this is where the relationship between fibrations, homotopies, and foliations starts to become more explicit. Fibrations, foliations, homotopies, and completions becomes more explicit.
Right. So I mean, the basic point here is you're saying we can actualize a foliation by saying, not only do we say all those things in that layer we consider to be simultaneous or something, but let's actually make them identical by having a completion that brings them all, that connects them. Is that right?
Right. Exactly. And as I have some examples of that later on. But okay, this is some kind of boring category theory stuff. Okay, this is the thing I was saying about. I mean, so if you have an object that naturally has a groupoid structure, like a Rullian multiway system does, then when you construct fibrations of it, those fibrations inherit a topos structure. And that topos structure means that you can locally turn morphisms into isomorphisms without changing the global structure of the system.
Okay, I need to understand that better. By the way, we have a variety of questions on our live stream which indicate that we probably should just give a little bit more introduction, because we dived deep into meta-mathematics or something, into a combination of, what the heck is this a combination of? Collection of replacement rules, which are implementations of the axioms of the mathematical theory. Right, so go through to wherever.
Well, here's
J-random
a nice example.
mathematical theory. Right.
So group theory, here it is represented as replacement. Here's like associativity represented as patterned replacement rules.
Right. Okay. Right. So it's a multi-way system. Right. So and then the issue is, in that multi-way system, and the picture you've got there is of a single proof.
Right.
And there's a question about termination on the live stream. For this single proof, what we're doing is we're saying find a path from this particular term to this other term to prove that they are equal, and that by definition is a finite size thing. Well, assuming there is a finite path between those things. Okay, but what we're saying now is we're considering the meta-mathematics of all possible proofs. And for that, and hopefully I don't know whether you made it yet, the thing that will actually stub a picture from the full multi-way system to put the stubs in that correspond to this picture here.
No, that wasn't relevant to what I was writing, but I can do that.
Well, right, but I mean, so the point is that the triangles represent things that are branching off into branchial space, basically.
I mean, we did discuss. I mean, we covered. Hang on, how that works somewhere. Not sure. Is it in this bulletin? Or is it in this post?
You might want to enable dynamics so we don't see as many gray boxes. Right.
Somewhere
So
there was a discussion of that.
right. I mean, we got close. We didn't quite do it though.
Right. So
But what we wanted to do there, that picture there, what we wanted to do was to make the stubs, because effectively what's happening is at every one of those branch points there, what is happening, if I'm understanding correctly, is that in the full multi-way causal graph, there should be causal connections to other branches, right?
Right. So each one of these critical pair diamonds is an indication of where this particular proof path is plumbed into a larger collection of proof paths in the overall multi-way system.
Right, but I'd just like to see how that works, because I think that's going to be.
I do have some examples like way later on. I do have some examples somewhere of how you peel off individual proof paths from the multi-way system and how they correspond to the associated proof graphs and things. But it's, I don't know, it's kind of an obvious correspondence.
Well, let me see. So that's the multi-way graph, multi-way causal graph. I mean, that's an evolution states graph, evolution causal graph rather.
Yes.
Right. Okay. So now let's see how that peels off. So that there.
So every causal edge becomes a dashed edge where you're using a particular construct in the proof of some future substitution lemma. Every evolution edge becomes a... But
wait a minute. Those green things were Big Bang events, right? Those are initialization events. Those don't come from. Right. If you go back to your original picture, I mean.
No, that's not true.
Okay. Well, where do the green things come from?
They're axioms.
Well,
so
that's what
these replacement rules.
Yes. But okay,
but so those aren't Big Bang events. Big Bang events are the ones that are the initialization events that produce the initial.
All right, I was thinking of those. All right, that I see. Your point is what you're doing there is they are sort of Big Bang. They're Big Bang rule events in the sense that those things are the rules that are going to be applied over and over again. But here we're indicating their provenance by showing, the green thingy, the green shield or something that then feeds into that. The feeds in saying that edge. I mean, that is defining that arrow there is saying that the dotted line above it. Sorry, that green thing is really the identification for which rule was applied in the dotted line above, correct?
Well, it's specifying which construct the rule came from.
Yes, I understand, but the rule is the dotted line that joins one yellow circle to the next yellow circle.
Yeah.
Right? But this is a little different from what we're normally drawing, because normally in our normal multi-way graph, we do not draw the rules as, the only thing we draw as rules coming from somewhere else are the causal edges that connect our events. So a more direct correspondence.
The orange things.
Exactly. But
that was what I was saying, right? So the solid lines are the evolution edges, the dashed lines are the causal edges. That was the point of these pictures.
Okay, but why isn't there a solid line? Why is there no... It's a little odd that there are solid lines coming from the axioms.
Why?
Because I would have thought that the axiom would have a causal edge. The axiom is the thing from which the event comes.
Or the other way around. The axiom is the thing to which you could apply an event from a substitution lemma. In the linear case like this, it doesn't matter which way around it is.
I know it doesn't matter. But right. All right, fine.
Right.
I mean, do you have a more sophisticated example of this that isn't just linear?
Well, yeah. I mean, that was the point of doing this whole discussion over here. But what I was going to talk about before that was yes. So it's the inheritance of the topos structure from the groupoid structure. Right.
Okay. Let me understand that. So the point is that as you apply these completions, you apply the sort of full set of completions to implement No, I'm sorry, we got off track here, because what you were saying was, given a particular foliation, you can, in a sense, actualize that foliation by adding completions that give you mappings between the equivalent states, the states that are made equivalent by the foliation.
Yeah.
Is that correct?
Right. So as you can see here, for instance, right, this is a pair of terms that are not related by the axioms, but one can add an additional relation, and then what that corresponds to, if you then actualize it in terms of model theory, is a relation like this, which causes two branches to effectively behave as though they're one branch. Right, you're taking two branches that would otherwise have been independent in the free object, and you're constraining them so that now.
I understand, but if you go back to your foliation picture, what is
induced by the model?
Okay, fine. All right. So the equivalence relation.
There's an equivalence relation, just like in space-time. There's an equivalence relation of space-like separation, right? There's the equivalence relation of simultaneity, but there's also there's a unidirectional relation defined by time-like ordering. That's all we're saying.
Okay, but so here, let me just understand, because here the time-like order is a deduction, but you are making, you're turning that into an isomorphism somehow that can go both ways. Is that true or not?
Yeah, eventually, but I mean, for the time being, if that's seeing as that we didn't get,
we still didn't really discuss the groupoid inheritance thing. For the time being, we can just treat it as a morphism. It doesn't matter.
Okay, but you're saying the completions actualize those morphisms, basically.
Right.
That given a particular foliation, you have a bunch.
All right. Hello, everyone. We are back trying to talk about metamathematics and its relationship to our physics project. The surprising unification of, in a sense, the dynamics of mathematics and the dynamics of the physical world. And this is the notebook that Jonathan was using last time to talk about the, in a sense, just to summarize, and Jonathan should interrupt me as appropriate, but the basic idea is our multi-way systems can be thought of, the rules, the underlying rules for the multi-way system can be thought of as the, just as they can be thought of as the operation of the rules of physics, they can also be rules of mathematics, that is the application of mathematical axiom systems. And so in a sense, this is, so one interpretation, and again, we need to get these a little bit straight. One interpretation here is that what we're thinking about is theorems show the equivalence between things. So for example, these might be two representations, these might be a representation of a word in a group, and this connection here might say, according to the axioms of the group or groups in general, that word is equivalent to this other word, and therefore there is a theorem that says this is equal to that. And then there is a progression of sort of what's equal to what that you get by following down these paths. And that's kind of, and then the idea is to encode a sort of a base axiom system as the underlying collection of connections here. And I had examples of this even in the NKS book of doing things like that. Then, new idea, the notion is to think about foliations of this graph as corresponding to models of the underlying system. So in other words, we're saying based on the underlying axioms, we can deduce that this turns into this, that this is equal to this, and so on. But now, if we add a model which essentially allows us to, which essentially coordinatizes this picture, this is sort of an arbitrary coordinate system we're using here, but that coordinatizes this picture, then we say that that coordinate system says that anything that's below something else in this picture follows from or is equal to that. Now I'm already in an equality relation. Is that Jonathan or Xerxes, is that what we're saying here or not?
Well, I mean, this distinction is why I spent so long talking about, clarifying the distinction between the groupoid structure and the topos structure, right? Where one is simply localizable and the other one has isomorphisms everywhere. So in the localizable case, it's possible to turn implications into equalities, but in the groupoid case, it's, all the implications are already equalities. That's the clarification.
Sorry, say that again. Say that again. For the groupoid case, I understand that what we've done is we've turned every one of these into a two-way thing, right?
Right. So because the sort of fundamental structure that we're dealing with, which is the Rulio multi-way system, has a groupoid structure, but by design, so to speak, and because every other structure can be viewed as being either a foliation or a fibration of that Rulio multi-way system, they inherit not a full groupoid structure, but a topos structure, in which it's not the case that every morphism is an isomorphism, but it's the case that the topos can be localized, so you can convert a subset of morphisms into isomorphisms.
Okay, so when you say, so generally, these one-way arrows are thought of as like the morphisms of category theory. A two-way arrow is like an isomorphism.
Yes,
now,
exactly.
When you say, okay, so let's just zoom out for a second. The Rulio limit, which I'm claiming is a little bit like some kind of normalization group fixed point or something. The Rulio limit, let's just understand how that arises. The Rulio limit comes when you say, for every one of these, instead of having this particular rule, Livestream is asking about this foliation. This is just a toy example. What we're showing here is just a toy example. This is not a, the real thing is much wilder than this.
Right. I have
This
some
is
actual
just-
examples in my bulletin. But,
Okay. Should we look at them? Should we?
yeah, if you'd like, it's up to you.
Let's do it. Let's do it. Let's do it.
Sorry, let me share. Okay, let me know if anything is invisible. But
So far
okay,
it's visible.
so yeah, okay. So this is the thing I was saying about completion limits, right? So this is an explicit homotopy between paths here, right? Which is representable as a critical pair completion between every pair of points here.
Right. So
And-
so
and-
that. Okay, hold on. Let's just walk slowly through this. So this is saying we've got a completion which on its face would just complete a single branch pair would just remerge a single branch pair. But when we add that rule globally in, it produces this knitting, this more global knitting of those paths.
Well,
correct?
no, not quite. I mean, so what's happening is you're inducing this is a sequence of critical pair completions you're inducing by defining this homotopy between these paths.
Oh, I see.
Then-
I'm sorry. So,
Then when you add those in as completion rules, then you get this structure which has that homotopy, but it also has other more global effects.
okay. So I was wrong about the level. So I could have.
Yeah,
what I
this is the
said
thing you were talking about.
Was right. What you could have done instead of doing that homotopy between those paths that were of length whatever they were, 5 or something up there, if you just done the length 2 homotopy, you would have gone. Then you would have still got a globally knitted thing down below, because by implementing that homotopy, you are, as a completion, you're having a global effect on the system.
Yes, but it just wouldn't where so this point is associated to that point, this point's associated to that point. But if we picked a tipped foliation, it would be different, as I'll discuss later. And so this is where the relationship between fibrations, homotopies, and foliations starts to become more explicit. Fibrations, foliations, homotopies, and completions becomes more explicit.
Right. So I mean, the basic point here is you're saying we can actualize a foliation by saying not only do we say all those things in that layer we consider to be simultaneous or something, but let's actually make them identical by having a completion that brings them all that connects them. Is that right?
Right. Exactly. And I have some examples of that later on. But okay, this is some boring category theory stuff. Okay, yeah, this is the thing I was saying about. I mean, so if you have an object that naturally has a groupoid structure, like a Rulio multiway system does, then when you construct fibrations of it, those fibrations inherit a topos structure, and that topos structure means that you can locally turn morphisms into isomorphisms without changing the global structure of the system.
Okay, I need to understand that better. By the way, we have a variety of questions on our live stream which indicate that we probably should just give a little bit more introduction, because we dived deep into meta-mathematics or something, and into a combination of, what the heck is this a combination of? Type theory, meta-mathematics, physics, and something else. By the way, do we have Matthew on the yes, we do. Who hopefully is able to respond to some of these questions. Okay, might be useful. Oh gosh, there's a bunch of questions. But I hope Matthew can respond to some of these questions, because these are going to take us. Let's just do one more pass through what the basic idea is. Okay, so the basic idea is a mathematical theory is represented by a collection of replacement rules, which are implementations of the axioms of the mathematical theory. Right. So go through to wherever.
Well, here's
J-random
a nice example.
mathematical theory. Right.
So group theory, here it is represented as replacement. Here's like associativity represented as patterned replacement rules.
Right. Okay. Right. So it's a multi-way system. Right. So and then the issue is in that multi-way system, and the picture you've got there is of a single proof.
Right.
And There's a question about termination and live stream. Let's, for this single proof, what we're doing is we're saying find a path from this particular term to this other term to prove that they are equal, and that by definition is a it's a finite size thing. Well, assuming there is a finite path between those things. Okay, but what we're saying now is we're considering the meta-mathematics of all possible proofs. And for that, and hopefully I don't know whether you made it yet, the thing that will actually stub a picture from the from the full multi-way system to put the stubs in that correspond to this picture here.
No, that wasn't relevant to what I was writing, but I can do that.
Well, right, but I mean, so the point is that the triangles represent things that are branching off into branchial space, basically.
I mean, we did discuss. I mean, we covered. Hang on, how that works somewhere. Not sure. Is it in this bulletin? Was it in this post?
Want to enable dynamics so we don't see as many gray boxes. Right.
Somewhere here there was a discussion of that.
Right. I mean, we got close. We didn't quite do it though.
Right. So
what we wanted to do there, that picture there, what we wanted to do was to make the stubs, because effectively what's happening is at every one of those branch points there, what is happening, if I'm understanding correctly, is that in the full multi-way causal graph, there should be causal connections to other branches, right?
Right. So each one of these critical pair diamonds is an indication of where this particular proof path is plumbed into a larger collection of proof paths in the overall multi-way system.
Right, but I'd just like to see how that works, because I think that's going to be useful.
I do have some examples, like way later on. I do have some examples somewhere of how you peel off individual proof paths from the multi-way system and how they correspond to the associated proof graphs and things. But it's, I don't know, it's kind of an obvious correspondence.
Well, let me say, so that's the multi-way graph, multi-way causal graph. I mean, that's an evolution states graph, evolution causal graph rather.
Yes.
Right. Okay. So now let's see how that peels off. So that there.
So every causal edge becomes a dashed edge where you're using a particular construct in the proof of some future substitution lemma. Every evolution edge becomes a...
Wait a minute. Those green things were Big Bang events, right? Those are initialization events. Those don't come from. Right. If you go back to your original picture, I mean.
No, but that's not true.
Okay. Well, where do the green things come from?
They're axioms.
Well,
so
that's what I thought.
Replacement rules.
Yes. But okay.
Those aren't Big Bang events. Big Bang events are the ones that are the initialization events that produce the initial.
All right.
State.
I was thinking of those. All right. I see. Your point is what you're doing there is they are sort of Big Bang. They're Big Bang rule events in the sense that those things are the rules that are going to be applied over and over again. But here we're indicating their provenance by showing, the green thingy, the green shield or something that then feeds into that. The feeds in saying that edge, I mean, that is defining that arrow there is saying that the dotted line above it, that green thing is really the identification for which rule was applied in the dotted line above, correct?
Well, it's specifying which construct the rule came from.
Yes, I understand, but the rule is the dotted line that joins one yellow circle to the next yellow circle.
Yeah.
Right? But this is a little different from what we're normally drawing, because normally in our normal multi-way graph, we do not draw the rules as, the only thing we draw as rules coming from somewhere else are the causal edges that connect our events. So a more direct
hence
correspondence.
the orange things.
Exactly. But
that was what I was saying, right? So the solid lines are the evolution edges, the dashed lines are the causal edges. That was the point of these pictures.
Okay, but why isn't there a solid line? Why is there no? It's a little odd that there are solid lines coming from the axioms.
Why?
Because I would have thought that the axiom would have a causal edge. The axiom is the thing from which the event comes.
Or the other way around. The axiom is the thing to which you could apply an event from a substitution lemma. In the linear case like this, it doesn't matter which way around it is.
I know it doesn't matter. I know it doesn't matter. But right. All right, fine.
Right.
I mean, do you have a more sophisticated example of this that isn't just linear?
Well, yeah, I mean, that was the point of doing this whole discussion over here. But I was what I was going to talk about before that was yes, so it's the inheritance of the topos structure from the groupoid structure, right? That's
okay. Let me understand that. So the point is that as you apply as you apply these completions, you apply the sort of full set of completions to implement. No, I'm sorry, we got off track here, because what you were saying was, given a particular foliation, you can, in a sense, actualize that foliation by adding completions that give you mappings between the equivalent states, the states that are made equivalent by the foliation.
Yeah.
Is that correct?
Right. So as you can see here, for instance, right, this is a pair of terms that are not related by the axioms, but one can add an additional relation, and then what that corresponds to, if you then actualize it in terms of model theory, is a relation like this, which causes two branches to effectively behave as though they're one branch. Right, you're taking two branches that would otherwise have been independent in the free object, and you're constraining them so that now.
I understand, but if you go back to your foliation picture, normally in a foliation, you're saying there is an equivalence. You're describing all things in a slice as being somehow equivalent. But here, what we're doing is we're saying things that follow from one slice from the next are equivalent. So I'm a little confused by that.
Well, there are two equivalence relations. That's the whole point, right? There's the equivalence relation of mutual independence from the axioms, and there's the equivalence relation of the actual total order induced by the model.
Okay, fine. All right. So the equivalence relation.
There's an equivalence relation, just like in space-time. There's an equivalence relation of space-like separation, right? There's the equivalence relation of simultaneity, but there's also there's a unidirectional relation defined by time-like ordering. That's all we're saying.
Okay, but so here, let me just understand, because here the time-like order is a deduction, but you're turning that into an isomorphism somehow that can go both ways. Is that true or not?
Yeah, eventually, but I mean, for the time being, if that's seeing as though we still didn't really discuss the groupoid inheritance thing. For the time being, we can just treat it as a morphism. It doesn't matter.
Okay, but you're saying the completions actualize those morphisms, basically.
Right.
That given a particular foliation, you have a bunch of new morphisms induced by the foliation, so to speak, which you can then actualize as completions.
Right. And that's ultimately the statement of the univalence axiom, as interpreted in our models, right? It's the statement of equivalence between foliations, fibrations, and completions.
Say that again. I missed something there. So,
Completions are equivalent.
You might want to hit the save button. Yeah. Okay. So let me understand that. So let's go through this. Okay. So a foliation is a foliation of the sort of the raw symbolic mathematics multi-way graph. That's what you mean by that, right? That's the kind of thing we're doing here.
I mean, inducing a total order on the partial order induced by proof theory.
Okay, fine. Okay, the fibration you're talking about now is a fibration from the limit point groupoid, infinity groupoid. Is that right?
Well, it could be any it could be a fibration of any structure.
Well, explain the fibration in this context here. So I think I understand.
Yeah, I mean, that's what I was doing, right? So this object has multiple branches. This is a free object that has multiple branches.
Yep.
If we wanted to, we could fibrate it, so we could only consider a subset of those branches.
Yes.
Right? As an individual fiber, just like in the in the Rullial case we talked about sort of two sessions ago. And the point is, one way you can do that is by defining an equivalence relation between those branches, which is a completion. And the choice of which completion you make is determined by your fibration. And the fact that you can, that there is effectively an equivalence between defining a homotopy between paths and defining an identity relation between elements is what the univalence axiom says. So the fact that this is a fibration, that this can be induced by completion rules, and that this, the set of completion rules that you use is.
There might be in quantum mechanics, but there isn't in space-time.
Right, because in space-time you're not dealing with multi-way systems.
Well, I understand your individual experience is not a multi-way system.
Right. So you could have this is a sort of alien intelligences type discussion, right? You could have an alien intelligence that perceived space-time in the same way we perceive quantum mechanics, where they were effectively looking at elementary bifurcations in the space-time causal network and defining equivalences between those, and they would have a very different view of physics.
Right. So their view of physics would have no space.
Right.
The first approximation. It would just
except that they, in the same way as we see weird things that are the consequence of branchial geometry,
exactly,
they would see weird things that are consequence of spatial structure.
Let's just walk through that for 1 second, a little bit. Let's just walk through that for a second. So imagine that take the other case in which we were laid out in branchial space and able to consciously observe different parts of branchial space, which we're not currently. It's the statement.
Yeah.
So in a sense, we happen to exist in a single thread of branchial space and multi-threaded in physical space. And if we were single-threaded in physical space, there would be all these effects that come because we would say, gosh, look, there are these things that are coming. We're trying to complete everything down so that we only need to consider essentially our generational states in space. What is this? Okay, what is the claim here? That's.
So if you had observers who were localized in, or who were forced to collapse space-like separations down in space-time, but could move freely in branchial space, that analog of causal invariance would be multi-way invariance, in which you could take for each of the possible time-like paths through the causal network, there is an isomorphic multi-way system that you would observe.
Yes.
And so therefore, which would justify, implies justification for collapsing space-time, down to a single time-like path.
Okay, so let's understand why it is. Could we imagine, we sort of have only one path that we are conscious of in branchial space? Is that obvious it has to be that way? In other words, imagine that we had, our quantum AI, so to speak. This is going to make a good science fiction plot, if nothing else.
The quantum AI that maintains multiple threads of consciousness in branchial space.
Right.
Just as we can say, somebody could say, what do you mean? You have, somebody could say, you have completely different civilizations and different star systems? That's outrageous. Why aren't they just all, how can you perceive that there are two different civilizations and two different star systems? All we perceive is that there's a certain thread of time. But what would it mean? Let's think. So, no invariant causal partial order. Well, that's a yet different thing, right? That's an even higher level. But I mean, look, this is the whole point. This is the whole point. The thing that allows us to get reducibility, the thing that allows us to make sense of the world or of mathematics, is the fact that we are modding out by all of that. How did you get from here to there? If you don't do that,
I don't disagree. But why is this a strongest? It's the same statement.
Same statement as what?
As what you were just discussing.
I mean, definite things happening. You mean in
either there's an invariant causal partial order across all branches of the multi-way system, or there isn't. If there is, then all branches of the multi-way system can be treated as observationally equivalent. And if there's not, then they can't.
Well, you're saying, I see. Your point is, now I'm very confused, because your point is that there isn't a symmetry here between the causal invariance is operating in the multi-way space and not in physical space, which makes there be a different. It isn't the case.
No, it's not. It's not different, because you could define multi-way invariance, which operates in space-time, right? Where the induced multi-way systems for each time-like path are isomorphic. That was my whole point. And so what I'm trying to say is that an AI who sees multiple branches of the multi-way system that are not observationally equivalent by definition cannot construct a causal invariant representation of the world. Right? That's what it means for those branches to be inequivalent.
Just walk through this one more time. So what we're saying,
like I said, so either each branch of the multi-way system yields an isomorphic causal network, an isomorphic causal partial order relation, or it doesn't. So if it does, then you have causal invariance. There is only one branch of the multi-way system up to isomorphism, and that's to the best of our knowledge, that's basically
objective reality.
What we have, right? So what you're claiming is one where there isn't, where you have an AI which can simultaneously perceive multiple inequivalent branches of the multi-way system, which by definition therefore means that they can't have an invariant causal partial order.
All right. Okay. So your point is
they must be capable of tracking multiple possible causal histories at the same time.
No, but your point is, if the underlying rules of physics are causal invariant, then there's no possibility of a multi-threaded quantum AI.
That's part of my point here.
Right, so that point is, but nevertheless, the analog of that, there is a multi-threaded physical space AI. That's okay, because there is no similar notion of causal invariance for space. That's a feature of branchial space, but not a feature of space. That makes sense?
Not to me.
Okay, explain. I mean,
go on, sorry.
No, I mean, so the point is, since the multi-way graph is formed in, the extent of the multi-way graph, it extends in branchial space.
Yeah, obviously.
And if there is causal invariance, there is a single, as you say, there is a single, essentially, up to there's a single objective history to the multi-way, to what happens in the multi-way system. But if you look at the corresponding thing in space-time,
then you get multi-way invariance, which is this.
You're saying, if you said, confused. Let's
no, what I'm saying is really, really simple, right? So each, in the multi-way evolution, in the evolution causal graph, there are multiple causal networks, multiple space-times, one for each branch. Within each space-time, there are multiple time-like paths, right? The swapping the spatial and branchial directions yields the analog of causal invariance, which would be multi-way invariance, which says if you look at, for each time-like path, what is the associated causal network for that time-like path? What is the associated multi-way graph for that time-like path? You could ask, are those multi-way graphs necessarily isomorphic as direct acyclic graphs?
Yes.
In other words, is the branchial structure the same? And that's the direct analog of causal invariance for the multi-way system. So they're symmetric ideas.
Okay, so your point is, if you look at the causal graph in space-time, each path through that causal graph has a...
there are multiple copies of that path, right? That exist extended
in the
branchial
different
space.
parts of the multi-way
So you can look at the induced multi-way graphs for each.
I understand
for each such time-like path.
But I think it's not quite. There's a slight difference here. Okay, so let's just go through this. So this is saying, if you are looking at, if you live in space-time, then right now, if you look at a particular branch, I mean, the full thing is the multi-way causal graph, where you can look at it, project it onto space-time so that you're going down, so you're looking at the causal graph projected onto a particular causal graph associated with a particular multi-way slice, so to speak, of space-time. Now, what you're saying is you can project the multi-way causal graph in one of two directions. You can either say that you're going to look at these, you're going to take as, I mean, yes, I think this is what you're saying. You can project it either way around. You can either say you've got and either way around, the other direction in it looks like something that has a for which you can ask the question: is there a what does causal invariance mean, and does causal invariance mean?
But it's not causal invariance in this case. It's evolution invariance, multi-way evolution graph invariance,
which might not be true.
Just like causal invariance might not be true, right? But the whole point is, you're taking this multi-way causal network, you can mod out by one of two possible directions, and then you can ask whether the other combinatorial structures retain isomorphism.
Exactly. Yes.
I don't see why there's an asymmetry.
Well, in our way of describing, that if you say you're looking, the main thing is the multi-way causal graph, you can project it either in a spatial direction or a branchial direction. I agree.
Okay, cool. Yeah, that's all I was saying.
But I mean, we have made more claims about causal invariance than about multi-way invariance. We don't think, I think, that multi-way invariance is true, whereas we think it is plausible that causal invariance is true. And what you're saying is, even if, you have made the claim that even if causal invariance isn't true, we'll make it true by doing completions as a result of the way we observe things. And you're saying, just like if we were, so I'm just trying to walk through what it means, because we have a better understanding of spatial, of physical space than a branchial space. If we were these organisms that were essentially doing spatial completions, right? What would that look like? What would that be doing? What that would be saying is, it would be like what we do in statistical mechanics, like the coarse graining we do in statistical mechanics. We'd be saying we're coarse graining across these spatial directions. Right.
And it would be the alternative way of measuring, say, two halves of a bell pair or something.
Yes. Okay. Fair enough. But I mean, what we'd be doing is, what would actually be seen to happen is we'd be saying we are we're combining. So if there's causal invariance, right, then okay, if there was both multi-way invariance and causal invariance, then we have turned the universe into, I would say, an ODE or something. I mean, we've turned it into something where there's just a single thread of time, and that's all there is.
It's not just a single thread of time. There's one time-like path.
Yeah. But that's what I mean. There's one. There's no space. There's no branchial space. It's just. It's a. We've turned it from what you could think of as a big sort of PDE-like creature to something which is just a single variable, evolving in time.
Mm-hmm.
Okay, so it probably isn't. So multi-way invariance probably isn't true, and the argument is whether branchial
causal invariance is true and we don't know, and it probably doesn't matter much.
No, but the point I'm making is that just as we can induce causal invariance, we can and do induce multi-way invariance when doing things like teleportation.
Well,
so
I mean, if we could do genuine teleportation,
consider an EPR pair, right? So
yeah,
if they are spatially separated, and we want to produce a quantum measurement of the, we want to measure the combined quantum state of that system.
I understand. Then we have to
implicitly
do
perform a spatial completion.
Spatial completion. I agree.
Inducing.
I just don't have as much intuition
multi-way
about that as I might have about coarse-grained and statistical mechanics. All right, but anyway, so how on earth did we get into this discussion? We were talking about how did we get into this? We were talking about the significance of the univalence axiom for physics. So we're saying here that you're saying, given the underlying multi-way system, right? The claim is that a foliation which defines a total order a fibration which goes in that case. What is the definition of a fibration when it doesn't come? Okay, why is the univalence axiom? Why? Let me think.
So I don't understand the question.
Well, there isn't a well-formed question.
Right. I mean, the univalence axiom is the thing that allows you to treat these paths as being a single path, and therefore allows. So, for this four-branched thing, this four-branched algebraic structure that happens to be a finite group, there exists a foliation of this four-branched structure into three-branched fibers. Right.
Okay. I mean, it's not self-evidently obvious to me, but I mean, yes, I'm sure there is. You can just have a bunch of relations that combine branches.
Well, yeah, I mean that's kind of the point, right? It's hang wait. What was the old thing? Yeah, because so like in the case of a Rulliol multi-way system, right? So there exists a fibration into sort of multi-branched. Sorry, this is a large and dynamic notebook.
Enable dynamics, it'll help you a lot.
That tends to make things slower.
Well, I don't know.
Maybe it doesn't. Okay, what was I? Yes, okay, so there exists a fibration of this Rulliol multi-way system into multiple, I guess in this case it's 7-branched ordinary multi-way systems.
How do you know it's 7? Where did the 7 come from?
Because I explicitly constructed it, I think, to be 7. Wait.
Okay. I saw a 7 in there, but I don't know why it's 7 branches.
Something like this.
Okay.
And so all I'm making is the analogous claim here, right? So there exists a fibration into it.
Slow down a second. So we've got this Rulliol graph, and we're saying, what did you do to get that particular fibration?
Well, so in this case, I'm just cheating, right? I'm starting from the particular multi-way system I want, and then I'm highlighting that.
Okay, fine.
The point is, what would I have to do in order to construct this explicitly? Well, the only point I'm making is we could just take all the branches that aren't on this fiber and make them equivalent to branches that are on this fiber, right?
So in other words, you're saying you could collapse this this graph to its one fiber by either doing completions that just collapse everything onto that fiber, or by doing foliations which define equivalence classes that make everything orthogonal to that fiber slide down onto that fiber.
Well, my point is that they're the same, right? That's the whole context for this.
No, I understand that. The claim is that those can all be viewed as being the same. Now, right. But they are, in these finite systems, they are literally symbolically the same, are they not?
Yeah, right. But the point is you have to make one additional assumption to be able to. The point is, what's the difference between calling this a single branch and calling this 2 branches, but where you can kind of hop from one to the other? That
Okay.
involves making a statement that identity and equivalence are the same thing. That the fact that there is equivalence between AB and BA here on these two different branches means that we can treat the branches as identical is the statement of univalence.
And does that statement have more teeth if the thing gets infinite somehow?
Well, it's only non-obvious when you have a continuum system. It's not about infinite. It's about uncountability.
Right, because in this case, the treat them as identical is kind of like, well, sure, you can do that. But explain what would go wrong. What's the obstruction when you try and, what makes it non-obvious that you can treat them as identical when it's a continuous system?
Well, it's not obvious even in the discrete case, right? That's why you need an axiom of propositional extensionality.
What do you mean? Go ahead.
The notion that propositional extensionality should extend to systems which are not obviously propositional, like continuous topological spaces. That's where it gets non-trivial.
What do you mean propositional extensionality? You mean like the axiom of extensionality in set theory, or what?
Well, the axiom of extensionality is an example of extensionality, but proposition. So,
what is the general meaning of extensionality?
Well, extensionality just means when do you consider two things to be the same? Right. So the axiom of extensionality in set theory says you consider sets to be the same when they have the same elements. Propositional extensionality says that you consider propositions to be the same when one implies the other, when they mutually imply each other. Sorry.
A and B are
Could
identical.
You make a note of that, because I need to remember that.
Okay. So I think I already made a note about this, but I can make another one. So state equivalence function in general, mathematics.
Right.
So axiom of extensionality.
There's an example of that for sets.
Consider two sets equivalent if they contain the same elements.
All right.
Propositional extensionality.
All right. So. All right, what we had been talking about last time, and I know you want to talk about toposes and things like that, and we're going to get to those, but what we've been talking about last time is choices of foliations that correspond to, essentially the tipped foliations, and the idea that you could define a tipped foliation by just adding one relation, for example.
Right.
Right. So do you have an example of that now?
Well,
So,
that was this, right?
okay, but how about we can see that? Can we see that in a group?
Yeah. This is a group.
Okay. And so then you add, so there's a group, and let's just walk through for a second, both for my benefit and for people on the live stream. Could you scroll up, just show what the relations are that lead to this thing?
Well, we can reconstruct it if you like. So if we take multi-way group generators A, B, relations
You
that
didn't
start
make
with
strings yet.
they're, like I said in my email, they're all converted to strings internally.
Yeah, I understand that. I just worry about the trip into the interior.
In transit. No, it should be fine. Famous last words.
I think there are letters that you could use which would not be fine and which will just blow up completely. But anyway.
That'll be fun to see.
Okay, by the way, Nick points out on our live stream that we should update the glossary with all these mathematical terms, and he's right.
I'll send them in to be added.
Okay.
So here's
What the heck is that?
it's a multi-way system.
Okay,
So-
so show it in the non-layered form first before you confuse us totally.
Okay, sorry.
Okay, so this thing here is, let's just understand this. This is a free group.
Yep.
Okay, so why isn't this, let's understand what this picture is, which
So
is not my
one of the things
favorite. Yeah.
This is one of the things I'm really excited about because this is a new kind of object. It's a Cayley graph, but with additional proof theoretic structure, which I think is really cool.
Yes, I hate to tell you this, but I'm pretty sure these existed in NKS. I talked about this exact thing, and I had a whole elaborate discussion of why these aren't Cayley graphs.
Right, I saw. But as
Right.
far as I could tell, you did it for groups. I couldn't see any other algebraic structures.
You mean like what, like loops or something?
I mean, so what I've been doing is I've been gradually just translating all algebraic structures I could think of into these
I
things.
did it for groups and semigroups. I didn't even do it for monoids. Yes.
Okay, there are monoids, there are abelian groups. I'm working on rings and things.
Oh, cool. No, that is interesting. That's definitely interesting. But I just want to understand this picture for a second, okay? So could we just look at a smaller version with labels?
Yeah.
Or the 2 version, even the 2 version with labels.
I mean, let's do. Why not? Let's do the free group on one generator.
Okay. Okay, so these are the words in the free group on one generator.
Right, except that some of these words are equivalent.
Exactly.
So in the Cayley graph, they would be collapsed.
Exactly so. Right.
Yeah.
This is a structure that I also have long believed should exist. Right. And whenever I've tried to feed this to mathematicians, they just tell me to go look at the Cayley graph, which is this thing with all its pieces collapsed.
Exactly. It's a Cayley graph with a state equivalence function defined by the.
Right. So this is the unrolled. This is the unrolled structure of the group before it has been modded down by the equivalence relation, right? Before the word problem has been solved. This is the thing without its word problem solved.
But but you can still infer this. I mean, okay, obviously I'm preaching to the converted here, but you can obviously you can see the solution to the word.
That's a really interesting idea. But anyway, so you're okay. So I agree. That is essentially the actualization of the word problem, what you just showed.
Right.
And for example, by the way, in the NKS book, you will find the a group with an undecidable word problem, right? I think maybe it's a semi-group with an undecidable word problem, and you can make this picture with that. And what does it mean to have an undecidable word problem? It means that there are arbitrarily long paths that you have to follow that exist in this thing. Because the undecidability of the word problem is that you can't, that you have to.
That was a mistake. That was a big mistake.
I would suggest you interrupt it. I think that's.
I did.
Oh well, there you go. Okay, that's cool. It's a bit of a shame that it doesn't look more symmetrical. I mean, it's fairly symmetrical, but I'm sure the real structure is actually still more symmetrical. Okay, fine. So
the thing I wanted to point out was, so now let's take this and we could say highlight graph, I don't know, multi-way graph AB, BA. So that's there and there.
Nice. Okay,
so
now we're going to do the abelianization. Yeah.
Right, so if we lay this thing out, it's a partial abelianization. So if we lay this thing out in space-time, branch time. So what we want to do is we want to construct now a foliation effectively where, let's construct the foliation where, so A, B, and BA are not treated as equivalent with respect to this partial order, right?
Yeah.
But we can define a foliation in which they are, and we can simulate that by taking this thing and then adding, oops, sorry, accidentally brought up documentation.
Well, what I would suggest doing, the heck is that? Oh.
That's what happens when you click frame, apparently. And we do relations, AB equals BA. Then we get that.
Mm-hmm.
So this is the point, right? So that foliation, which would be a flat, that would be an inertial foliation because it's just one equivalence, which is then applied everywhere, defines this vibration of the system in which we treat these paths as we effectively define
this more explicitly. Let's go back and let's look at the full foliation, which means not just two things got to be identical, but we slice everything with that sort of slicing. Okay, so in this example here, where would we put the foliation slices? I mean, there's many different places we can put them, but what's the minimal set of places to put the foliation slices to get this inertial foliation?
Well, we just need we need slices where where
Can I
one of
suggest
these.
that you say aspect ratio to a half for that layered graph plot?
Sure.
Okay, I think that's more revealing, but only just. Okay, so now, okay, where do you think the foliation goes here?
Well, so anything where these lie on different hypersurfaces would be a valid such foliation.
Well, where those lie. Okay, so this is the claim. This is morphism versus isomorphism. There's a little bit of a story there, that it doesn't. That you're just saying that those lie. That those are not, even though in this picture, those appear in the same vertical slice, right? You're saying
they're no longer mutually independent.
Right, but what you're saying is we need some routing of the foliation slices so that those two things appear in different slices.
Right.
And your claim is that it's the only constraint. Other than that, we can do whatever we want.
Right. And so the point is, if we let that just be a general inertial frame, then so we know from these completion rules that if we just define rules that say, AB goes to BA, BA goes to AB, which is effectively what these relations are doing, it's not just going to affect that pair of states, right? It's obviously going to affect any pair of states that has an AB or a BA subterm.
Yeah.
So this foliation effectively gets extrapolated out to the whole rest of the multi-way system.
Well, but let's see how that works. Can we do that? Or how would we do that? How would we draw that foliation?
Let me actually get the code for this. Oh, this is where aspect ratios come back to bite us.
What the heck?
There we go. That's almost right.
Well, so you're saying that, but I don't know why this is a canonical such foliation at all.
What do you mean?
Well, I mean, why is this? What is canonical about this foliation? As
what do you mean by canonical?
Well, I mean, you're saying it's an inertial frame, but
yeah.
You're saying, and the reason you say it's an inertial frame is because there is a cosmological inertial frame which corresponds to the thing that is a certain number of a certain graph distance from the root, right?
Sure. The actual point I'm making is that this is how I define an inertial frame, right? So that where do I say this? Right, yeah, flatter inertial reference frames corresponding to what we might call free models when viewed as an algebraic structure. They're those defined by the axioms or by one additional relation. Right, so if you just define, if you just have the foliation defined by the axioms, that's the inertial frame. That's the cosmological rest frame. Then if you have one additional relation, that defines an inertial frame.
Is that a nice? I mean, does that work in space-time? Just having a single beta parameter, is that sufficient to define the notion of an inertial frame?
Pretty much, right?
Are you sure? I mean, let's think about that. But you're saying that, I mean, aren't there other one-parameter families that aren't inertial at all in space-time?
Not one-parameter families of, effectively angles of normal vectors in geodesic normal coordinates, which is all
yeah, I understand what that is, but is that what this is as well?
That's what I'm defining it to be. Obviously, this space doesn't have a geometry defined on it, so we're free to do what we like at some level.
Right.
I mean, I can make a note of that. So let's define cosmological rest frame as being the free model. Define
somebody is commenting that, wasn't it proved that there isn't a cosmological rest frame by the Michelson-Morley experiment? No, sorry. That was before the cosmic microwave background was discovered. It was the concept that there wasn't an ether, the concept that you needed an ether for electromagnetic wave propagation was disproved. The concept that there is a rest frame for the universe was absolutely not disproved, although at the time nobody knew that was the case. But in modern times, we know from the rest frame of the cosmic microwave background that there is a rest frame for the universe. And we are traveling at about 1/1000th of the speed of light relative to that rest frame.
Does that seem reasonable? That, I mean, obviously, in space time, you just need one.
Michelson-Morley, and so
you just need one additional equivalence between space-like separated events to define a global inertial frame. So in the same way, we define an inertial model as being one where there's one additional relation beyond the sort of background partial order induced by the axioms.
It's not 100% obvious to me that this thing about one additional equivalence relation between space-like separated events is sufficient to force the frame to be inertial. It's not obvious to me. I think that requires some kind of proof by actually thinking about. Oh gosh, maybe should be obvious.
Well, I mean, isn't the proof just a pair of space-like separated events defines an angle of a time-like vector in geodesic normal coordinates? That angle defines a global inertial frame by definition.
Well, but you've got to prove that it doesn't have acceleration.
What?
Look, an inertial frame doesn't have acceleration. Right?
I know what an inertial frame is. So, but that.
Why is it self-evident that the thing you've defined must force a metric that doesn't involve acceleration?
It doesn't, obviously.
What doesn't?
It doesn't force it. Of course, a single pair of space-like separated events does not force a metric that's non-accelerating, but it does completely define a global inertial frame.
You're saying there exists an inertial frame consistent with
for every pair. Yeah, there is a unique global inertial frame defined by a pair of space-like separated events.
That I agree with, but it's not sufficient to say that yes, that is correct. But it's not obvious.
But just like adding one additional group relation is not sufficient for proving that there's only one additional group relation.
Indeed, but the thing you get out by just adding one additional group relation, and that's what I'm complaining about with your straight foliation lines, that's in no way a unique foliation consistent with the constraint that it should put those two values, A, B, and BA in different slices.
But what? Yeah, but that's the beauty of it, right? So if you only add one additional relation, if there's only one equivalence made between space-like separated events, then that gives you the only thing that you can uniquely define is a global inertial frame. If you have two equivalences between two different pairs of space-like separated events, then you start to get into the realm of accelerating frames and curvature and things like that.
No, but there are many different slicings that are consistent with the total order that you're defining here, right?
Right.
Right, but I mean, and this is just one such frame as the one you're drawing, but it is not obvious to me that that frame as you have drawn it does not have weird accelerating features.
I'm totally confused. Okay, so we are the only type of frame that is uniquely specified by an equivalence relation between a pair of space-like separated events is a global inertial frame. Are we in agreement about that?
The only one that is uniquely specified, that has no other, that yes, but but the constraint that you're giving here is compatible with many non-inertial frames.
Yeah.
The only frame that is fully specified by this is an inertial frame.
Yeah. So just like, as I say, the constraint that there is this additional relation is compatible with many other possible finite sets of relations that don't contain a single element.
Yeah.
So
Sure.
what's the problem?
You're making the claim that that you can immediately deduce from, look, what I'm complaining about is the drawing of these slices, which I claim is non-unique and not obviously consistent with it being, not obviously being, the fact that you can identify those 2 points and say these define an inertial frame, no problem. The fact that these slices that you've defined, which entail lots of other relationships, are the inertial frame associated with those things is not obvious to me.
But that, I mean, that's what I'm defining it to be, and like I say, because of this, it's exactly consistent with the definition of an inertial frame in relativity. I'm confused as to why it wouldn't be.
I have to think about it some more. I'm not, you might be right, that it's sufficient to define it as that.
I mean, I agree, of course, these foliation lines are a complete fake, right? Because this network is not laid out in the appropriate way. But that's not the point.
Okay, I don't think okay, but the main issue here is what we're saying is there exists a foliation which records these new relations that have been added. And you're saying, and we think of that as, okay, so what is the relationship between a model? You're saying, as we add more relations, we are homing in more precisely on, I mean, a model, to make a model, we could just say, we are coordinatizing the space, putting these terms at these coordinate positions. And when, one term appears on top of another term, it means that there's an equivalence between these things. That will be a sort of a fully specified model. You are edging towards models by adding relations, right?
Well, these are, we're edging towards a maximally non-free model by adding relations, if that's what you mean.
Yes, that's what I mean.
But even the free group is a model of the group axioms.
Fair enough. Okay, fair enough.
It's just, like I say, it's defined to be a model which satisfies no additional relations beyond the axioms of the group. Fine.
Okay, fine. So, but what I'm saying is that normally, you can, when you go far enough, so actually something I don't know, it's probably obvious. You take a group, icosahedral group, whatever you want, A5, whatever it is, right? And it has a certain set of generators and relations. Let's say you incompletely add the relations. What do you get?
A different group.
What's that?
A different group.
Closer to the free group. I see. But it might not be a finite group. That's the point. That's why we don't so much know about it. The point is you need a certain set of relations to guarantee finiteness. And probably by the time you've hit finiteness, even then, you might go further. Okay, so fine. So what will happen is you start with a free group. You keep adding relations. The thing will, at some moment, it will become a finite group.
Right.
Yeah,
sorry,
go ahead.
No,
Can
so
you show that actually here?
Well, no, I was just going to say, and obviously we have the model of the free group, and we also have the model of the maximally non-free group. Well, in fact, actually, I have a picture here somewhere. It takes a moment to render because it's quite a complicated object. But basically, you take some algebraic structure, you apply all possible Knuth-Benix completion rules to it, and therefore you get the maximally non-free version of that algebraic structure because it's now that structure. It's the free version of that structure in which all possible relations have been applied.
And how does that relate to the Rulio graph?
Well, that's the point, right? So the Rulio graph is the maximally non-free object. That's why we consider it to be the fundamental structure. So this is an example of a group to which every possible relation has been applied. So it's the maximally non-free group.
Right. But now that object, if we looked at the Cayley graph of that object, it would just crush down to one point. Am I right?
Right. Everything is equivalent to identity. Ultimately.
Right. So all the life and times of this thing is in the non-manifest equivalence of different words.
Right. So the obviously the fundamental point, I mean, it's kind of obvious, but we should probably note it anyway. The free group is maximally quantum mechanical or purely quantum mechanical. The maximally non-free group, i.e., in which all possible relations/completion rules applied is purely classical. All normal. No, normal is a bad. All I can't say regular. Ordinary groups lie somewhere on the quantum classical spectrum.
Yes. So this Rullial structure is basically the Rullial structure of an arbitrary binary operator with inverses and so on. In other words, what else does it have? That Rullial structure has the underlying group axioms.
But I mean, here's the interesting thing, right? So in this, again, preaching to the converted, I know, but the nice thing about these objects is that ultimately they don't make a distinction between the group axioms and the relations, just like, because multi-way systems don't make a distinction. In fact, they don't make a distinction with the generators either. The generators are just unidirectional relations. And so the point is, it doesn't, once you get to this structure, just like it doesn't, once you've generated the Rullial multi-way system for some model of computation, it kind of doesn't matter what the underlying model of computation was. By the time you've generated this thing, it doesn't matter what the underlying axioms were. The point is every algebraic structure that can be defined as...
I understand, has a limit point, which is this. Its limit point under repeated completion is that.
Yes, exactly. And so by extension, every algebraic structure that's based on sets with binary operations satisfying some axioms is a fiber in some appropriate fibration of this space.
I agree. But the fact that it's binary operators is important. This thing, the geometry of this thing will be different if it's not binary operators.
No, exactly. So which is why I'm actually quite excited to produce the ring version of these. Once we start looking at rings and modules and algebras and things, it'll get more.
I mean, so what we got. Yes, I agree. So okay,
anyway, I have to say, I'm just stunned by how beautiful like the free abelian groups are.
Okay, let's look at a free abelian group.
So generators, relations none. E.
How much does it matter that the thing is a subgroup rather than a semigroup, by the way?
A little bit. Well, we can see that explicitly. Hang on.
Make a 3D picture.
Do 3 steps. It'll get more interesting.
Yeah, it's interesting. But now just do graph 3D of that.
Okie dokie.
Oh, no. Just make another picture. Don't destroy that one. Just say graph 3D of percent. And then we're going to look at the abelian semigroup.
Right. Yeah. Oh my gosh.
What the hell is that? What is that?
I don't know. Hang on. Let me do. I think this might get. I forget which one it was that had some very nice symmetrical structure. I mean, obviously,
that's going to be huge. That's going to be huge. Stop. That's going to be absolutely huge.
We shall see.
Okay. Okay.
Give it a moment. There we go.
That's nice.
It's lovely. Yeah, I really like this.
Yeah.
There's some nice wall arts to be made here.
Okay, so anyway, but this is the rulal, this is the completion limit.
Well, yeah, sorry, this isn't. This is just the abelian limit. But so to answer your question, if we take a multi-way semigroup, let's do generators, AB,
Quotes, right.
relations none to states graph. So the semigroup is kind of boring if we don't have any relations, right? Because it's just each element kind of acts completely independently. But if we start to add, I mean, do you want to take the abelian case? So if we do something like that, then it starts to have a more interesting structure.
Right, but by semigroup, you are going both ways, because the natural multi-way system is a semi-semigroup.
What?
The natural multi-way system.
What is a semi-semigroup?
It's one where the relations don't go both ways round. Where?
Oh, right. Yeah. Okay, sure. No, they do go both ways round in this.
Okay, fine. So your thing is defined to go both ways round.
Right, because it's a semigroup.
Okay, so can we just see the corresponding picture there for multi-way group? Just the exact same thing. Just make a copy of that. Just make a copy.
Oh yeah, sure.
Just did.
So, but we also need to do DE inverses XY.
And multi-way group. Multi-way group.
Oh yeah, good catch. That gives you some indication.
Okay.
Well, of course, abelianization. Did you want to see the abelianized version? Because defining AB equals BA doesn't abelianize this, right? Because we also have to, because there's AB and there's X.
Yeah,
and
sure.
Y.
There's more. Yes, right. So we really want the abelianized version.
Okay. Well, the abelianized version is just the free abelian group, right? That's just do states graph structure. That was the thing we were looking at earlier.
Jose on our live stream says he's actually written a paper about the free abelian group.
Oh, cool.
Cool.
And as an intermediate, we could say multi-way monoid. Well, actually, let's do the free case first.
So this is all going to give me a further complex about the NKS book, that everything that was in there that was partially explored actually needed to be taken further.
Okay, so that's the free case of the monoid. But then if we do, well, actually, I should create functions for doing abelianized versions, because I don't have that right now. But that would be useful.
Okay, that's not
equals EA. BE equals EB.
And you have E squared equals E already.
Yeah, well, we could do that as well. Oh, sorry. No. This is the problem with using symbols. Yeah, that is a problem with using symbols. But, it should have E squared equals E anyway.
Yeah, okay. All right, so let's zoom out back again to what we're talking about. So we're talking about the fact that, okay, so we've got this notion of models, and we've got the idea that we can make these foliations that add equivalences effectively. And your claim is that the univalence axiom is the statement that we can as well mathematically, I mean, I still claim that the fundamental point of the univalence axiom is mathematics only cares about answers, it doesn't care about working. That's the fundamental statement. In other words, you can, once you've established an equivalence, you can throw away all the working inside. Do you agree with that statement?
That's an implication of it. Yeah, I agree.
But the question is, what's the essence of? I mean, so in physics, it's like saying you can
See, when you say it's an equivalence, what you're saying is you can deduce things about the world by, even if you've coarse-grained, you can still deduce things about the world.
Yeah, it's just coarse graining, right? I mean, that's the essence of it. It's that once you know the macro state, you can throw away the microstructure.
Right, but the fact that you can throw it away, the reason that is a meaningful statement, the reason that's a consentful statement is...
Yeah, it's because you care about the theorem more than you care about the proof. And
what I'm saying is that you can then build your mathematics doing only that. Similarly, you can build your physics looking only at the coarse-grained states.
No, I agree.
Right, but so it is not self-evident, and it is a consequence of, causal invariance or the two statements. Either there's causal invariance or there are observers who induce causal invariance, and either way, it's sufficient to look at the causally modded states to know how to build the physics that you care about. And similarly, in the mathematics, what we're saying is it's sufficient to, operationally, what it means is, in doing mathematics, you care about theorems, but you do not care about proofs. To build your mathematics, you can, once you've proved something, it's like the Tetris game. It's already disappeared, and you can go on and build further in the tower. Is that a fair characterization? I'm just trying to get an intuitive understanding of what this means.
Like I say, I think as we talked about last time, I agree. That's an implication.
Right, but the question is, what is it about mathematics? Because the fact that mathematics is doable, right? If it wasn't for that, in studying cellular automata, I want to contrast the mathematics of studying cellular automata with mathematics as it is normally done. And, I think it's
because mathematics builds up lemmas and CAs don't, right? That's what you're saying.
That's what I'm saying. What I'm saying is that in CAs, you care about the innards of what happens. It is not sufficient to just say, this is the input-output pair, so to speak.
Yeah, I think we all agree on that, right?
Okay, but I think that's
mathematicians define lemmas.
Yes, I understand. It may be obvious, but I think it's a fundamental piece of philosophy of mathematics which had not been understood, at least by me, before now.
Okay.
Right. Define lemmas, and cellular automaton operatives do not, so to speak. Okay, but then what we have been coming to last time was, we were close to having a good understanding of the analog of special relativity in these things. And so let's just recap that. So the analog of special relativity is the statement that there are, different frames correspond to different relations being added. Right. So, so we're saying that given that's the statement. Let's walk through that claim, but we can also walk through the claim that different frames correspond to different foliations that correspond to different additions of relations, and we're saying that the basic claim is you're claiming that this quantity is invariant with respect to that. That is, you can either verify the theorem by walking down the explicit proof graph as defined. What are we calling this? It's basically the multi-way graph. But what is the mathematical statement of that? The explicit abstract proof graph, basically. Or you can say, let me define a model, verify the model. I'm not sure what the analog of verifying the model is. And in space-time, we don't think there's anything to verify. In the case of an inertial frame, we're just like, it's okay. We can set up an inertial frame. I guess that's in Minkowski space, so it's not obvious.
I don't understand it. So, well, in GR, it takes irreducible computational effort.
Yeah, to confirm that you have a valid choice of foliation.
To determine that the points in your claimed space-like hypersurface are in fact with the causal partial order.
Indeed, it does. Right. But the question, okay, so I just want to, okay, in general relativity, I understand that what you're doing there is to trade off the establishment of a valid sequence of spatial-like hypersurfaces with which is the model validation, against the actual sort of following of these edges. But let's see, that there are more things that are true. Okay, but what is the analog of special relativity? What is the analog of the Minkowski? Or isn't there one? Or is it only... What's the analog of special relativity?
Well, the statement as reduced to inertial to inertial models, right? And, models with only one additional
I know. But is there a clean version of that? In other words, can we quantitatively derive what is the analog of the quantitative, 1 minus v squared over c squared? What's the analog of E equals mc squared?
Well, with E equals mc squared, I don't really understand what you meant by the derivation of it in the space-time case, given that it's a definition. But
it's not a definition. It's a definition of rest mass. But the question, but there is an intuitive sense of a rest mass.
Sure.
Right. That's the question: is whether there is a definition here that, sort of aligns with the intuitive notion of a rest mass. So I mean, the question is, look, in general, I don't even know okay, again, special relativity. Is there a clean notion of special relativity as opposed to general relativity?
Yeah.
Okay. So, and your claim is that is the one relation case.
Yeah.
Okay, well, let's see that. I mean, so if that's really right, then it better be true that one relation. So what's the analog of velocity?
What do you mean? The analog of velocity is the distance in the proof, is given by the distance in the proof space of the two sides of that relation, obviously.
Well, it's saying that the two sides of that relation, let's imagine that we put them in two successive elementary time slots. Is that going to be our velocity? That we take the spatial distance in proofs? No, it's not right. It's not quite right.
Why not?
It's not quite right. Okay, look, proof space. Okay, first question is, what's distance in proof space? Okay, distance in proof space. How do we measure distance in proof space? Answer: we have this multi-way graph. Okay, defining points, presumably. Let's okay, so this isn't quite the same thing. So okay, go ahead.
What?
No,
I mean, I'm recapping what we discussed last time. The number of necessary.
Well, okay, so this is distance from the root is a coordination which is essentially like the time in the cosmological rest frame. Right?
Right.
This is, so you should write that down. You should make a note. This is time difference in the cosmological rest frame. That's the difference between two terms. The time
this
distance
is an
between two.
invariant proof time interval.
Just to be clear, that this is the distance that you have to go down in the multi-way graph to get from one term to another, right? But now, what does that have to do with? Okay, fine. So that's
what is it? This isn't a distance. This is a coordinatization.
well, it's also a distance. It's a coordinatization if you start it from the Big Bang at the beginning. How does it give additional coordinates? It's giving one coordinate, right? The number of applications. You're saying that you take if there was only one axiom, it would just be a linear order of how many times you have to apply that axiom.
Yeah.
Okay. So if you have
If
multiple
there are
axioms,
then you have a high dimensional space.
Okay, so let's walk through that. So that if it's a binary tree, for example, the leaves are labeled by binary numbers. Right, that's the analogous thing. Correct?
Okay. Yeah.
You agree? I mean,
Sure.
That's so we have two theorems, two axioms, 0 and 1, and each leaf is labeled by the sequence of axioms you need to do to get to that leaf.
Yeah, I understand. Yeah.
Okay. So let's again. I'm trying to understand what is the derivation. How can we derive? Is there a quantitative version of a Lorentz transformation in this case?
Yeah.
Okay, what is it?
It's the Lorentz transformation. It's the thing that preserves the this invariant interval.
Okay, but can we write down what the formula for it is? So in terms of that proof time distance, right? We have we have the speed of light, which is the maximum proof speed.
Yeah.
Right. So what is our formula for, can we write down what? I mean, we should be able to write down.
Transform.
Okay, but so
the Pythagorean theorem holds in Hilbert spaces of any dimension.
Yes, I understand. But so can we figure out what it actually means in this case? Right, so you've made a claim that the relation, we can describe what the velocity corresponding to a relation is by looking at the distance spanned by that relation, effectively.
Sure.
Okay, so what you're claiming is, if we look at the distance spanned by that relation and we compare it, how do we compare that to the, quote, speed of light?
I don't understand.
Look, there should be, okay, so listen, if we're trying to get, for example, time dilation, which you're claiming you would get by taking successively in your model, in your setup, right, as we take modding out relations that span larger distances, what we will be getting is essentially higher velocity frames, right? Yeah. Okay, so it should be the case that as we get to a higher velocity frame, that when we do that the essentially proof time necessary goes up by this Pythagorean. Okay.
Yeah.
Okay, so that will be an interesting thing to see, because it is a quantitative relation that we get by saying we are picking a particular relation. That then implies something about the number of steps that we have to go through for a particular proof, right? It's saying...
I agree, which is why in the very first live stream I mentioned it would be interesting to find out what the model theoretic analogs of slowdown theorems would be.
Right, but so let's see what it is.
I'm currently working on.
Okay. So this is okay. So this is not a totally stupid question. It's just you haven't figured out the answer yet.
No, I agree. It's not a totally stupid question. That's why we asked it several days ago. I'm wondering what the. I mean,
because I'm slow and I work on other things in between these live streams. but let's go back to this again for a second, because I think we actually could kind of crack it, right? So what we're saying is there is a certain distance. I'm just saying, what is the comparison? There's a certain distance in this metric, right? You've got a multi-way graph. You can label every node in the multi-way graph by a possibly redundant sequence of, it's essentially the word length well, it depends how you set it up, but in the multi-way graph, every element can be labeled by its essentially part number in how you got to it, right?
Yeah.
Right, which is in general redundant. There may be multiple paths to it, but there is a shortest such path. Right, so you could label it if you want to label it with different axioms, or you could ignore the different axioms and you could just say it's such and such a number of steps from the root. Right, makes sense. Right, so what we're saying is a given, two elements which are joined by a completion, by a relation, right? They will each have certain coordinate positions in that coordination, right? Yeah, right. Okay, so now we've got two, elements which you are going to conflate with a completion, right? With a relation, and they are at two different coordinate positions, right? They're about to be conflated. They will define, in your claim, a frame, right? That corresponds to, that has certain effective velocity. If those proof relations were, okay, so here's a point. If those proof relations were time-like, if those terms were time-like connected, right, then that would be the equivalent of a speed of light transformation.
No, it would be a superluminal transformation. If they were light-like connection, it would be a
fine. What does it mean? Okay, so what would it mean for them to be light-like connected?
Well, that's what we discussed last time, right? And that's what I was writing up here. So here, if you consider an elementary proof cone, you can consider the extremal points just like you would in an ordinary causal network. So then the light-like paths are the non-constructive proofs, the ones which require infinite computational efforts in order to witness the associated model. And the internal ones, the time-like paths.
Yeah, right. But I'm just trying to understand. Okay, I just think there is going to be some formula that basically just tells one, in terms of the distance between things which are being connected in a relation, there will be some quantitative formula that tells one the effective slowdown in proof. Right, and that formula would essentially tell one, as one looks at a theory, right, as one turns a knob to change one's theory, right, that's going to tell one, as you add axioms that effectively connect more and more distant points, or more and more, closer and closer to time-like connected points. What does that mean intuitively? As you connect those things, I would expect that it would make proofs go faster, but it doesn't. It makes proofs go slower, according to this. What's going on there? In other words, okay, I would have expected that if you make a lemma that lets you jump ahead, for example, in my Boolean algebra thing, right?
Which it obviously does, right? Because you're increasing the theorem, you're decreasing the theorem verification complexity by increasing the model verification complexity. That's why I wrote this down.
Okay, but so intuitively, what one's saying is, by adding a lemma, which is a jump ahead lemma, you are effectively, why does that, what's confusing me is time dilation is normally something where things happen more slowly, right? It takes more steps. Oh no, I see the problem. The problem is the definition of the time coordinate.
You appear to be going more slowly, but time passes more quickly for you.
Right. That's what I'm confused about. Right. So the answer is
you're decreasing the theorem verification complexity, as I said.
Right. So what you're doing is
you're trading off theorem verification complexity for model verification complexity because by adding in the lemma, you're reducing the length of the shortest proofs, but you're adding in an extra step in verifying that that additional lemma is in fact compatible
Yeah,
with
I
the
get it.
original
But I
axiom.
mean, so intuitively, what you're doing is you're by adding a sort of jump ahead in the theorem network, right? You are making it faster for you to get further in the theorem network. But to somebody looking from the outside, that means time is passing faster for you, but you right, but so what does that mean for what is the outside observer? What is the observer at rest in the mathematical and metamathematical world? What is the observer at rest as compared to, so the observer at rest is saying,
Is the free model.
no, I understand that, but the observer at rest says that oh, your time is passing. Why does the observer at rest say time is passing slower for? Oh, I see. Because they are able to get further in a given time, that means time is passing slower for them. Yeah. Okay. That's right. That's just exactly the same. And but then the claim is there is a quantitative connection between time. Yeah. All right. Okay. I mean, I still think there's some actual, v squared over c squared thing. But do you agree, or do you think that that's not correct? That there's an actual, you can actually measure this, as in, you can actually measure.
No, of course.
But
of course you can.
Right, but so you should be able to see it. For example, in other words, what this should do is, gosh, we might even have the data for this. In the NKS book, needless to say, I did this thing of adding lemmas, right? Adding,
which is the thing I did here.
Okay.
So what you can shorten proofs by adding. You can achieve a speed up of 3 steps by adding only a single lemma, at the expense of increasing the computational complexity of verifying that the lemma you added was compatible with the original set of axioms.
This means that as you add lemmas, so this is kind of like the speed up of mathematics, so to speak. As you add lemmas, the question is, as one publishes more theorems, what does this mean? How should mathematics speed up as more theorems are published? And what?
As the technical sophistication of mathematics increases,
aka more theorems are known.
Right. AKA more theorems known. A generalized graduate student